This is Solarman. Today I'm going to help you understand one of my awesome invention, that is the Solarman rocket. But before that, I would like to explain about how we can use a rocket to travel to space. Now, where is space? Space is where there's no air. As we rise up above the sea level, at 5 kilometers, air is thinned by a factor of 2. I traveled to Tibet once and I saw a bag of tiramisu become inflated with a double volume because the air is thinned by a factor of 2. Now, as we rise further, for example, when we travel in an airplane, we rise to about 10 kilometers, twice that of Tibet that I went to. And what happened is that air is thinned again by a factor of 2, and now air compared to the ground is thinned by a factor of 4. Now, if you ride on a helium balloon, the highest you can rise up to is 50 kilometers, which is 10 times that of the Tibet plateau at 5 kilometers. So how much is air thin? Well, it's thin by a factor of 1/2 times 1/2, and there are 10 1/2 there, which is 1 divided by 1024, 1 in 1,000. So air is already very thin and get to the point that the helium balloon can't rise anymore. Now, according to von Karman, space is defined as above sea level by 100 kilometers. Now that is where you have twice the distance to where the hot air balloon is. So air is thin by 1 in 1,000 for the helium balloon, and then when it comes to space, it's 1 in 1 million. 1,000 times 1,000 is 1 million. So there, air is so thin that you can't use your wing flying through air to create a lift so that the airplane won't fall down. And that's defined as space. Now, the second question is, now that we know where space is, how do we get there? First, you have to get out of the atmosphere, rising up to 100 kilometers. And for that, 1 kilogram of mass would take about 1 megajoules of energy to rise up to that level. A lot, but not really a lot compared to the amount of energy that's needed to accelerate yourself so that you can stay in orbit. Even if you rise to space at 100 kilometers, gravity will still pull you down. So you need to circle the Earth at a speed that is 24 times the speed of sound, or about 8,000 meters per second. If you calculate the kinetic energy per kilogram, it will take about 32 megajoules of energy to accelerate a kilogram of matter so that it stays in orbit. So compared to the potential energy, the kinetic energy is 32 times, much more than that. So speed matters to stay in orbit. And today we're going to talk about how you can go to space in 2 different ways. Now, you probably know that Virgin Galactic is competing with Blue Origin to take people to space. Now, Virgin Galactic used a spacecraft to go to space, but it doesn't reach orbit. It doesn't reach the speed of 24 times the speed of sound. Basically, at the ground level, you use a double airplane with the spacecraft put in between so that it rises to about 10 kilometers. The Virgin Galactic would fire its rocket engine to go to about less than 100 kilometers, and you're supposed to be reaching space, and it gradually fall back down to Earth, and the rising up and then falling back down takes about less than half an hour. So you would feel gravity free for about half an hour, and they charge you $250,000 for that. Blue Origin is a little bit different. It uses a 2-stage rocket engine, and the first stage is about this length, and you put a capsule for 4 people on top of the second stage rocket engine. So it fires up, drop in about less than a minute or 2. It drops the first stage, and then the second stage rocket fires, and then you reach again about 60 to 70 kilometer height, and then you experience free fall, and you fall back to Earth using a parachute. Okay, So that's how people claim that you can do space tourism, but you really don't stay there too long because you just want to experience weightless condition for about half an hour. Now, to reach orbit and stay there indefinitely takes a lot more than just energy. It's not just 30-some megajoules of energy per kilogram to reach orbit, but it's more important. The more difficult part is the so-called curse of the rocket equation. This rocket equation basically say the orbital velocity you need to reach 24 times the speed of sound is equal to exhaust velocity of the liquid hydrogen and liquid oxygen combustion, and that's 12 times the speed of sound is 24. So orbital velocity is about twice as fast as the exhaust velocity, and the curse of the rocket equation is that you need to throw away so much matter that only a very small percentage, about 10% of the mass that you have when you reach orbit compared to the launching mass, including all the fuel and liquid oxygen, is only about 10% of the initial mass. So the mass ratio in this case would be 10, and the logarithm of the mass ratio is less than 4. So less than one, a lot less, actually less than 10% of the mass would reach orbit because you're throwing away so much material. Now I can explain this very simply by showing this. Now initially, for example, this is the first stage rocket and this is the second stage rocket. Now, let me assume that you throw away the first stage rocket instantaneously. So this go out because it's mostly rocket fuel. It goes out at the velocity which is 12 times the speed of sound, Mach 12. Now, because action and reaction are equal and opposite, so half of the velocity, namely 6 times the speed of sound, go this way, and 6 times the speed of sound go this way. So by dumping half of your mass and burning this half, you would be able to accelerate the first stage rocket to only 6 times the velocity of sound, and that's what we're going to see later. Now, in order for you to reach 24 times the speed of sound, you need to do this splitting 3 more times. Already, the second stage rocket is reaching 6 times the speed of sound. Then you split it in 2. This part that goes on further would be 12 times the speed of sound. You split this further, it will go to 18 times the speed of sound. And split it further, it will go to 24 times the speed of sound. In that case, you would reach orbit. Okay? So involve 4 times of splitting and throwing away things at 12 times the speed of sound so that the remaining half would reach 6 times the speed of sound, okay? And doing that 4 times would allow you to reach 24. And in this 4 times splitting, only 1/16 of your mass from during launch reach orbit. So that's a very low ratio. Now, I'm going to show you the launching of the Starling satellites on the Spacex. This first stage rocket is like 2/3 the size, and the second stage rocket is about 1/3 of the size. In about 4 seconds, it will start to launch, and I'll describe to you these meters. This is a speed meter. So right now it's launching. It is rising very slowly, but the speed increased very quickly. Now it's already 100 kilometers per hour at 10 seconds after launching. Now the next event that's very important is reaching the speed of sound, Mach 1. Now it would go to about the altitude of about less than 10 kilometers, and the speed meter would rise up to about 1,234 kilometers per hour. Now this is already 40 seconds. You start to see that the rocket is tilting because it doesn't go straight up all the time. It's tilted very rapidly. So around 50 seconds. Now 52, 53 seconds after launch. Now it's 1 minute after launch. You reach an altitude of about 8 kilometers and it reached 1,200 kilometers per hour, which is basically the speed of sound. So that's the first event. It's about 1 minute. It reached the speed of sound at around 10 kilometers. Now it will go on further, it's tilting further. The rocket is firing. The next event is so-called the maximum pressure event. where the atmosphere is thinning up as you rise further to about 20 kilometers, but the pressure on the nose cone of the rocket is increasing because it's going faster and faster. So at the max pressure, which is about now, it faces the maximum Q. This is max Q. It just passed the max Q at this point. Lift off max Q, okay? And Mach 1 is about here. Now I go on further, and around 2 minutes and 2.5 minutes, it shut off the main engine. Basically, it has exhausted all the fuel of the first stage rocket. You will see that the rocket engine will shut off, and about 10 seconds later, the first stage rocket hardware will fall back to Earth, pretty much empty of all the fuel that it has. Now, right now it's 2 minutes and 20 seconds, and at the altitude about, we'll see that it would shut off the main engine at an altitude of above 60 kilometers at a speed that is about 6 times the speed of sound. You see the exhaust is exhausted. And now the first stage rocket at about 6 times the speed of sound, about 70 kilometers above the Earth, is falling back to Earth. Now you see here, it will start to fire the second stage rocket. Now you saw that basically what fell away was the cover of the nose cone, okay? And then it starts, after the nose cone is dropped off, and they do recover the nose cone, and then they will start the second stage rocket. Now, the amount of propulsion is very small compared with the first stage rocket. You see here, it reached 100 kilometers for the second stage rocket. It has to go to about 200 kilometers above the Earth to release the Starling satellite, and the speed is increasing. Now, right now, it's slightly more than, it's at about 9,000 kilometers per hour. It's about less than 8 times the speed of sound. So it's still a long way. It's only 1/3 at 8 times the speed of sound to go to 24 times the speed of sound. So in terms of speed, it's still a long way to go. But in terms of the amount of rocket fuel that you need, is not a lot, okay? So we're going to leave this alone now that it reached about 10,000 kilometers per hour. To reach orbit, you'll have to go to almost 30,000 kilometers per hour at an altitude close to 200 kilometers. Let's now look at the first stage rocket. You see that it spits out some propellant once in a while in order to adjust the trajectory to recover the first stage rocket. It has 2 pads here. Basically, they control airflow so that it can steer the rocket down onto a platform that you can't see at this point. It's further down. The altitude now is about 100 kilometers, which is smaller than the 140 kilometers that the second stage has gone up to, and it's not dropping very fast, but the speed is not slowing down very fast either. Actually, it's increasing. The reason why speed is increasing is because gravity is accelerating it. So in order to slow down, because 7,000 kilometers per hour is a very high speed, so you need to drop it down to about 6,000, and so that the gravity will not keep on accelerating it. It will start to fire some of the rocket fuel remaining in the first stage rocket in order to slow it down, okay? And very soon you will see that it start to fire. It's still adjusting its trajectory by moving these pedals as well as using the propellant. Now, at the altitude of about 90 kilometers above the sea level, you will see this fire at a speed that is about 7,000 kilometers per hour. Now, it's still accelerating, largely because of gravity. It's accelerating, pulling it faster and faster. So you need to slow down. All right. So its entry is where you have the entry burn. You see this entry here, meaning that the second stage satellite, the first stage rocket is approaching the point of entry, where at the point of entry we fire at the rocket engine. Now we're going to see this start to enter into entry, and once it got to entry, it fires the first stage rocket. Now it starts it burns the rocket fuel in the first stage rocket. It burns for about 20 seconds, very short, and it's coming out of the entry point. And at the speed, the altitude is dropping down fairly quickly because it's almost dropping down vertically. And the speed has decelerated down to about 6,000 kilometers per hour at an altitude of about 40 kilometers. It shut off. At this point, the re-entry of the first stage rocket that they reuse later is done by means of the resistance of air. As it's falling, air is fairly dense now at an altitude of only about 20 kilometers. So air is about 1/16 times as heavy as on the, so it provides substantial resistance because it's still going out at 3 or 4 times the speed of sound. So air is creating a drag effect, and you see basically is now below 10 kilometers and under 2,000 kilometers per hour. Whereas you have seen that this has the second stage rocket has speeded up almost to 20,000 kilometers per hour at an altitude that is 170 kilometers. It's not yet to 200, it's not yet to 30,000 kilometers per hour, 24 times the speed of sound here, but it has gone 2/3 of its way in this sound. Now, notice here, it's going to start the burn of the so-called landing burn, because it's coming down, and even though it has decelerated the speed of about 600 kilometers per hour and it's dropping very quickly, you need to launch it vertically. So you need to see it starts the burn of the engine, so they land on the pad. Now it has landed. The first stage rocket has landed. The speed is 0, the altitude is 0, so it reached a landing point. So the second stage rocket go on accelerating towards its final orbit. Right now it's about 26,000 times kilometer per hour, and it's above 20 times the speed of sound, and it's about to reach orbit when it gets to about 30,000 kilometers per hour. But we're not going to see that, and the video ends here. So after watching that video, I learned a lot, because I think we need to design a first stage propulsion system and a second stage propulsion system, whereas the first stage propulsion system has about on 1/2 of the mass of this, or even 2/3 of the mass of the second stage propulsion system. The first stage propulsion system would take the second stage to an altitude of about 50 kilometers above the Earth, and also at a speed of 6 times the speed of sound. And after that, the system, the first stage propulsion system would come back to Earth, land by itself by means of a parachute and its own guidance system. And then the second stage would go on to reach the orbit. I will describe in a later video my design of the solarman rocket that has 2 stages of rocketry. And wait till then. I hope you understood rocket science, and I hope that you would like and subscribe to my channel. Until next time, this is Solarman.